So we're the FAA, 44,000 people, our mission, safest air system in the world. A lot of money, a lot of jobs, 12 million jobs. We'll talk through today a little bit of what our background experience is. I was going to give you a little background on NextGen. I have a lot of slides in that area that I'm going to kind of flip through and not talk to so much as I'm going to run a video that kind of gives you the background on NextGen. So rather than put you to sleep with a bunch of slides, I'll run a video. The slides are, the slide references in place where to look for more information is in the slides, and if you happen to have an actual electronic copy of the slides, I had hyperlinked them, although ALOC probably took them out on me. I work with ALOC a lot. So. Some helpful acronyms. I don't think most of them do too much of a deal. I thought the one on ADA was important. Yes, the Earl of Lovelace is in, as I understand it, up Ross-shire, which is not too far from Aberdeen, I guess. So we have obviously a big control of the air traffic system of the world, about 60% of the air traffic. What helps to understand is that we're in these so-called domains, meaning there's kind of different offices and groups responsible for different areas. So on the ground, in the terminal areas, in the en route cruise phases, we also have some groups that do things such as trying to do the traffic flow management, which is to collect the data and reschedule flights, realign flights, get around weather, things of that nature, traffic management units. So we're kind of organized in these three main domains and a couple of smaller ones. Weather group was recently absorbed into one of each of the domains, what used to be separate, for example. Can I be heard? I see him making adjustments. What's the problem? We're the best, right? USA. So we have very old technology that we're still trying to replace. We're in the process of trying to do that with ARAM, and we spent a good couple of years working through growing pains with our user groups in terms of, well, the old system did it this way, and the new system does it that way, and oh, by the way, we like the old way. And that system evolved piecemeal, making it very hard to modify and maintain because we had these thousands of lines of code that had been cobbled together, sometimes with PR patches instead of real thought-out changes. And the inefficiencies then in the overall air traffic system, because we can't modify it for the future, the old system, we end up with traffic congestion, delays, loss of predictability, and technical obsolescence. And because our program we're working on now, ARAM, which is the replacement for the NAS host in the en route domain, is behind schedule. We're actually spending money to sustain a old IBM mainframe now in the NAS host position for another year or two past its economic life. So the impact of an automation failure starts to back up the system. So whether we start putting ground delays on, we start putting miles in trail, which means we keep airplanes a little bit further apart, a little distance apart. And obviously, if there's air traffic system failure in a region, we can't be sending planes into that region. So we'll put them in holds outside, queue them up, rack them, and stack them. ARAM is supposed to be the solution, and it will be the solution. We actually have it in service at a couple of centers today. In 2007 at the SIG-ADA, when I talked about this, we were reaching system tests and completing system tests with the prime developer and had to go through all the operational level tests. We had to do some up-leveling to deal with legacy things and how they had evolved while we were in development and things of that nature. Key aspects of this was to separate the mission critical and the non-mission critical. Becomes kind of relevant in my later talk. But the purpose of this was to eliminate the system downtime, provide more flexibility, and protect ATC services from any type of failure, and provide a scalable platform to do all the wonderful things that we want to do, which is going to be next gen. And we've actually started on some of those programs. I talked with someone in the hall the other day about ADSB, and actually in the library last night, and pointed out that actually we have ADSB, the initial implementations, automatic dependent surveillance broadcast, in the ARAM system is kind of queued up waiting for us to get the main system through its operational trials and fully accepted so we can deploy the entire country. There's 20 centers and 20 ERAM systems that are combined to provide the U.S. air traffic. I left a few of these charts in. I wasn't going to speak a lot to them in case you were interested, just to show you that it is an ADA-based architecture for the applications. The infrastructure is a mix of ADA and C, C++. There's a few pieces of applications that were actually built up from existing NDI-type components, like the Raytheon Tracker, which was C, C++. But altogether, we have in the neighborhood of about 550,000 lines of ADA in the operational system. Actually, probably it's around 600 now because we've actually been growing as we've done some user changes trying to get through acceptance. And the overall system size, including its support systems, is about 1.5 million lines of code now. I threw these in. I just recently gone through all this. It's been a big challenge. One of the things I'm sure you're seeing, we get a lot of security concerns, a lot of security issues. And one of the things I was able to point out and try to bring to the CIO was that, well, we try to pick technologies for security rather than using, they wanted us to do scanning after the fact and find our vulnerabilities and put a POA and M together in order to, eliminate or correct the problems we found during this post-development process. And I said, well, that's all well and good. I said, but we tried to pick technology up front to try to give us a better security. It doesn't guarantee us security. It doesn't mean we don't have to do other things, and it isn't worthwhile to do certain types of scan. He just didn't have the right tools for scanning us. When he got all said and done, because of our environments of AIX and ADA, out of the 1.5 million lines of code, I was able to scan 800 of them for his tool that the chief information officer had acquired to use for scanning for security vulnerabilities. But this is the core or kernel of our environment, that key technologies that we depend upon and that we monitor the health of and support. Again, just another chart from that same sort of presentation showing, that we think it through from the outside in and the inside out and try to build that in. So next gen, the future. Right now today, as I mentioned, we have ERAM in 2 centers operational, but we're about 2 years behind the schedule. So we had requirement deficiencies from not understanding what was in the legacy. How many people have had that problem? I've heard it talked about a couple of times here. LDRA gave a presentation where they pointed out that happens all the time. We had operational issues with new designs. We intentionally changed some things. We decoupled some things. And we changed some concepts. And in the process of doing it, the user groups look at it and say, well, but now, for example, a controller can now see beyond his control border up to 50 miles if he's adapted it and configured it that way. So now that I can see it, I feel like I have to do something about it. And so I need certain features and capabilities to understand that traffic that I'm seeing across the boundary that I'm responsible for. Errors in design and implementation, not unexpected in a system of that size and complexity, that we're going to screw some things up for no reason than the fact that we just didn't do it right. And legacy impact. One of the things you find with the legacy is that the procedures the operators use become so tied in with the way the legacy does it, even if the legacy doesn't quite do it right or doesn't quite do it in the best way. So you then redesign it and say, oh, well, intellectually, academically, this is the way this function should work. I'll take this equation and I can calculate exactly how it should be. And they'll all shake their heads and say, yes, that's the real world. That's what the airplane is doing. But the reality is that the old system couldn't do that, so they've learned to adjust, they've set their procedures that way, and now they say, but your system doesn't meet my procedures needs. It becomes in a different answer to my old system. And so then you get into, well, is it a retraining issue, or do I need to look more like the legacy? And in some cases, depends on the politics of the day as well as the technical issue of the day, how important it is to them. We end up modifying to look more like the legacy, even though it may or may not be more algorithmically correct. Coming up, big items in an ADSB, we have, like I say, a system that will go out in the fall, or probably operational testing in the spring of next year, that has ADSB for the Gulf of Mexico to Quayside. And the one I'm going to talk about somewhat today is the SWIM, which is the Information Management Program. Its intent is to be able to make flight data ubiquitously available to all the users, airline operations centers, customs enforcement, a whole host of users who want to see and have that data. One of the challenges we have is that once you advertise you're going to do this, because we're intending to do this with a web service, other programs and project managers start saying, well, I can leverage off of that. Well, if you're a high reliability area of the, and I'll talk about that when we get there, then you shouldn't leverage off of something that was designed for low availability, low reliability. And so you start seeing them pile on, and so requirements start piling on. And users start adding requirements and expectations because, well, if you're going to do this, then, as an operator maintainer, I need to be able to see this type of data real time, and you haven't planned for that. And so that's caused some problem in that program. And I think this is where I'm supposed to switch, right? And see if I'm smart enough to do this.
As an airline passenger, you may barely notice the changes taking place over the next 10 years to improve your flight. But you will appreciate the increased safety, environmental benefits, and reduced delays as the next generation air transportation system is adopted. To best illustrate the benefits of NextGen, let's first look at how your flight, say from Los Angeles to Washington, is managed today. As your plane pulls away from the gate and gets in line, your pilot is talking to controllers in the LAX tower for critical routing information. After takeoff, a TRACON controller steers the pilot through maneuvers to rise thousands of feet while covering about 100 ground miles. At about 23,000 feet, your pilot talks to another controller at Los Angeles Center, who directs the plane to its final cruising altitude of 35,000 feet. Across the country, your plane follows other planes like cars on an interstate highway. As with cars, the route is dictated by what's on the ground. Your plane must pass over radar fixes, generally not the most direct path. And every time the plane crosses an airspace boundary, your pilot changes radio frequencies more than 25 times cross-country and makes adjustments in the flight, speeding up, slowing down, and changing direction. Bad weather over, say, the Midwest will force your plane into inefficient flight paths and keep other planes on the ground, creating delays that ripple throughout the country. When your plane begins the slow descent into Washington, your pilot steps down, levels off, and speeds up, while also moving around to safely align with other traffic on the way to the runway at Dulles. Now, let's look at how NextGen will improve your flight. Improvements kick in as your plane leaves the gate. Surface traffic management on the ground makes things simpler, safer, and more orderly for both pilots and tower controllers. For one, they spend less time talking to each other on the radio. This reduces communications errors as digital data communications, similar to text messaging, expedites clearances. The order of departure is set automatically, reducing long waits and enhancing safety. As the plane heads to the runway, pilots and controllers each have a real-time GPS map of all ground traffic with such tools as ADSB and ASDX. This greatly improves airfield safety through a reliable shared view of the plane's surroundings, particularly during bad weather. During takeoff, precision RNAV and RNP procedures allow multiple departure paths from each runway, which increases airport capacity. This same precision gets your plane quickly out of the busy lower-level airspace to cruising altitude while saving fuel. At 35,000 feet, GPS-enabled RNAV, RNP, and ADSB allow planes to fly closer together without any loss of safety, which increases airspace capacity. Meanwhile, aircraft fly more direct paths that account for wind, destination, traffic, and weather. Weather, which now accounts for 70% of delays, becomes less of a problem. That thunderstorm over the Midwest that causes so much trouble today will be easily handled when shared network-enabled weather information is fused into decision-making tools through SWIM. Data communications, so useful in the airport, is also useful in the air, as it reduces radio frequency congestion, errors, and delays. As your plane lines up for arrival with other planes, its place in line is planned hundreds of miles in advance. Instead of the current step-down approach, tailored arrivals and then continuous descent arrivals allow a smoother descent into the airport. The more precise landing paths allow a steady descent with reduced power. This cuts time, fuel, noise, emissions, and holding patterns. As your plane comes in for landing at Dulles, Data Communications relays the runway exit point, assigned gate and taxi route to the pilot, so you quickly arrive at the gate doors, exit the plane, and pick up your luggage. As a next-gen passenger, you may notice a smoother flight, but what really gets your attention is being on time more often. You also know flying is safer and more fuel efficient, and that's what matters from gate to gate.
So that's the vision for about, well, I guess it's about 12 to 15 years out before it's all done. And I have some information in here. I didn't want to spend a lot of time on it, but I'll run through it. It talks about some of the individual pieces and parts. All of these have one thing in common. They're all going to be software intensive. They're all going to require a lot of data that's currently in one system to be available in all the systems and to integrate these components and these data. It's going to be a challenge in the technological sense and a challenge just in the management, program management sense, the human sense, of trying to pull all these pieces together. Because in addition, the other thing that has to happen is that all the operators and users have to be trained and retrained to deal as new pieces come in. So the strategy is to kind of bite off a piece at a time, taking on little projects at a time and pieces of the final capability at a time, both to prove them out as well as to get the infrastructure kernels in place. And that's kind of the path we're starting down now in the near term. We'll talk about that in a minute. I brought this slide over from a prior presentation, the 2007 presentation. I kind of said, well, what do I need? From a software perspective, you know, can I maybe use some Visual Basic, you know, that'd be good enough? What qualities, capabilities do I expect out of the software product and the software products? So obviously reliability, integrity, fault tolerance, all the sort of things we talk about in real time, highly reliable, highly available systems. And increasingly important in correctness is not just that it's tested and operationally safe to use, but I think we're moving down a path where we understand the cost effectiveness of being able to do more proof of correctness during development rather than waiting for this big year-and-a-half, 2-year test program after we think development is done to tell us all the things we screwed up. Again, here's the next-gen sort of programs, ADSB, automatic dependent surveillance, basically airplanes talking through satellites to tell you, here I am, and here's where I'm going, and here's my airspeed, and here's my current rate of turn. Collaborative air traffic management, that's that, trying to find ways to integrate all the data in order to queue up our aircraft in the most efficient manner possible as they come into arrival streams, address departures and address, you know, urgent needs to change the traffic flow and the traffic patterns, whether it be weather or because of something from an airline needing to cancel or add a flight. Next gen weather, the datacom, that's the one you hear about, the digital data communications, new voice switch, and then the SWIM program. Oh, not blown up? Okay, sorry about that. Thank you. So one of the things is they, I think they were trying to get me not to wander around. I'm normally a walker. You know, I'll be all up and down all over here. But they put me so close to the slides I can't look back at them and see what I'm talking about. So I have to look at my screen. So and that makes me stand in place because I can see my slides. I was on the train this morning and I'm like, okay, I hope I can see my slides because I don't remember what the hell I said. Excuse my language. Near-term evolutions in the air traffic system, and this now is becoming, it's not quite past tense because of the delays we're having in the base ERAM program. Again, we hope this fall to have the final operational service sign-offs done on that, and then we'll need to deploy that to the rest of the country, about 18 more centers, and in the process you'll start seeing some of these things are starting to go in, like the reduced navigation performance is in the current releases that are being tested, although there's always new enhancements and changes and ideas that are coming along there that we've been tweaking and adding to that for a couple of years. The big one, automatic dependent surveillance broadcast. We're going to have that in, again, deploy a software system this fall with operational testing in the spring down in our Albuquerque, New Mexico facility, and begin proving out the concepts of using that instead of radar. So in the meantime, we've got to not only handle aircraft that are still only have radar, you have to have the aircraft that have ADSB, and you have to have aircraft that do both, and then you have to be able to handle aircraft separation based upon, well, he has ADSB, he has radar. So these two aircraft, what is the criteria to apply to ensure I maintain the safe separation standards? And the system-wide information management, which the intention of which is to get the data out of each of the proprietary, those domains I talked about, terminal, tower, en route, the traffic flow, get the information that they develop and build out of their domains, make it readily available to other users of the system, as well as, for example, the airlines, or obviously there's going to be, there has been and there are programs now that allow you to go online and say, okay, where's grandma's flight, you know? And see real time, basically, where the latest report puts her at, or approximately anyway. Midterm, that's where the data communications, a lot of safety and security issues here, a lot of assurance issues here. One of the things that I won't talk about today, but I wanted to, but when I'm talking through the kind of SWIM, where we tried to use a web service type of interface to provide this ubiquitous available access to the data, the datacom come along and says, well, that seems like I need to see it in order to do what's called the context management, making sure that I validate that that airplane, that flight plan, and the airplane that I'm tracking through radio communications are the same, match them up, and have the context set that, for that aircraft. So I need the flight data for that. And they proposed to use the SWIM, and I started to say, well, whoever qualified these products for that type of a service, that's a high assurance, high security, high safety level, even though in its initial implementations, the performance and availability requirements don't drive that. Where we're going will drive that, and I questioned the architecture choice. Subsequently, because of problems in the SWIM, they've changed that approach and are going with a more direct interface, and it actually turned out saving them code to basically write it in a traditional interface. Our side will be Ada. The other program is using a mix of Ada and C++. I won't go through all those in detail. Again, I put some of these in here for information. Don't intend to read. Hopefully you've all learned to do that by now. Without my glasses, I'm beginning to not be able to again, and I'll soon be asking someone to read to me. So why SWIM? That's where I wanted to get to, which is we have this idea. Let's get this data out. What's the easiest and fastest way to do that? Well, the problem is that all these systems have their data locked inside themselves. They won't let anyone else see their data. You can't play in my arena, and the coordination necessary to understand, well, what, if you're in the terminal environment, you know, what the heck is that en route doing? Why is this airplane showing up at this location at this time with this, you know, it should be at this arrival stream. And to be able to coordinate that data ahead of time and coordinate that, especially through the traffic flow management, which is the one you see in the middle, where they would be able to integrate and say, you know, well, taking all of these flights, the optimum solution for departures or arrivals at this next location, or to go around the weather pattern in New York would be this. And then to be able to communicate any changes that requires first to the controllers, but then also to the pilots using data communications, presumably for that. And this is the motivator. So today we have all these pieces and parts of systems, and they all have interfaces. IP this, and you know, mostly TCP IP, although we still have some old legacy we're still trying to update and replace. And each one of these has an ICD, interface control document, which means it has interface requirements document, and it has, you know, a whole set of infrastructure and effort and time to support it. And as you start saying, well, I need to share more data, I need to connect the systems more together and get more data to more people, more places, you end up with the picture up in the upper right corner of this tangle of ICDs and IRDs crisscrossing each other and overseeing it. So the motivation is to say, well, if I can use a web service type of approach, a more new kind of SOA, service-oriented architecture, open architecture type of approach, then I can have each system define a set of data services that it can provide to others, establish a single interface that all other potential users or clients would then come through the one interface. It has one interface definition. It's in the web service description language that actually compiles into the final interface so that any updates automatically get shared, while you do have to address and deal with back level supporting in terms of the levels of the interface. The step up is much more straightforward, and I have really one web service description of the interface for each service or data service I want to provide, rather than for each system I want to connect to with that data. So using the service-oriented architecture, the intention is to allow these applications to locate and connect, share the data. In reality, unlike in web service, you can't just look us up and say, hey, let me see, you know, oh, there's the flight information service from the en route system. We do know we have to know our users ahead of time. But the intention is that if there's a new use, if another program or system or user emerges that says, I need access in this way, we say, well, here's the defined web protocols and interfaces. Here's client-related software that you can use to build your interface. And as long as you maintain these protocols, these security profiles, and we have you adapted in as a valid user, you can be up and running in a few months as a new server or a new client of our services. And so we started biting this off in little pieces, understand this technology. We're pretty used to being in our domain, you know, mission critical, real time, ADA, deterministic deadlines, our current implementation. We can detect the failure of most pieces of software in less than a nanosecond, basically at clock speed. We detect most failures, about 99-point-some% of failures. This stuff ain't that, so we better learn how it works. Now here's kind of some of the ideas and overview. The first one was to do what's called PDRRA, or pre-departure reroute, which is to say while they're on the ground. So I want to share data with the terminal, and who will share it with the tower as to their flight plans, and if there's a reroute necessary for weather, if the traffic flow management unit wants to reroute weather, they would basically send it in, we would actually see a visible indication of that. The controller would have an indicator saying, don't change this segment of the flight. It's been done by a traffic flow management unit. Today, that's done by someone bringing pieces of paper over to a controller and setting it next to him and saying, reroute these aircraft. And the idea was that this would show right up on his glass as an approved reroute action. It would have its initiative number and information to be available to it. And then it would be communicated back to the aircraft itself, since it's pre-departure, by the terminal data link, which is a data communications that's available in some airports today and is becoming available in the near future to the rest of the major airports for the aircraft to receive its clearances by digitally rather than by voice. And so we were going to build what's called the initial FIS, the Flight Information Service, to support that. The idea is pretty much to publish and they can subscribe. Well, we actually really wanted to provide them with the relevant flight data. And then we were also trying to get the initial capabilities to understand future services where we put a publish subscribe. You come in to subscribe for some classified set of data or some classes of data, once they classify. We can filter it to your request and then publish it to you and publish your interest in any updates. And that was the services that we went to bite off. I say went to bite off because we have a very preliminary capability going out. Again, this fall, it'll go up to Minneapolis and be put into place in operations sometime late next year. Part of that is the preference of the interfacing systems to wait until we have more of that system deployed before they'll bring their portions online. And because of the ARAM program itself being delayed, that pushes the whole schedule back by that. So it's a good year, year and a half behind its schedule because the ARAM program is behind its schedule. And what it's intended to do, provide traffic flow analysis tools so they can update flow and get it implemented and get it notified to the controllers at the terminal level, tower level, en route level, and get it to the airplane. Oh, and I did point out there that it is going out this fall as a software release, and we're still working through the details. Well, when will we start operationally trying to test it and integrate it and put it together? And that'll be in Minneapolis. The follow-on piece, which was supposed to be the broader, larger context, this was more of a, I won't say it's more than a proof of concept or sort of a system, but it's less than the full robust one center. It doesn't have redundancy. It does within its one location. The architecture will explain that in a minute. So we initial release in 2010, as I say, it's delayed. We're using the AIX operating system. The SWIM servers are using a Fuse program, which is a web services program written by Progress, or really it's not written by Progress, it's really the Apache programs with supportability provided by the Progress software company in terms of fixed support, maintenance support, tool support, and consulting and debugging. It consists of an enterprise service bus, the services framework, the mediation router, and a message broker. We've since eliminated it, but our original architecture assumed an Oracle database for COTS library usages. I think I point out later why we ended up dropping that. Basically, it couldn't meet our requirements as our requirements came to be known. A set of open source libraries and Java message service protocols. So the SWIM was going to use Fuse to establish a non-proprietary message channel endpoint for a SWIM consumer. An endpoint is basically what you think of as an endpoint, an IP endpoint. And you post that basically with, that's where they come post the requests for service for data. And the services framework and the routers kind of doesn't care who, where, why, what, when. If you're registered for the service, you have the correct WSDL for the service, it'll resolve all the transport and other protocol requirements necessary to access the service and return the data and maintain status of its performance. So in the enterprise service bus, Apache Service Mix is the core kernel behind that, and they support what's called the open OSGI. I always forget what the acronym means. But essentially, it's intended to provide a virtual address space or application container, and we call them containers, in which your various applications reside in the Java virtual model. More physical architecture here. The intention is that the swim would be in one location, other RCs would be connected, and then the other impacts are at our technical center. Physically, again, that shows a new connectivity coming out in the middle between the two, which is the swim services. Going at the very top, you see the new yellow box with the blue in it there, which is the swim server outboard outline. That one, again, was done, and I'll mention that, security drove some of those decisions to put it off-board, get it out of. Remember, we talked in ERAM, we wanted to separate mission-critical from non-mission critical processing in ERAM and get rid of them. All of a sudden now we're saying, well, this is important stuff, but it's not critical, but we need ERAM to provide it. So we said, okay, well, we'll adapt, write an ADA adapter around our current applications and have that send it to the Fuse product, which will then provide the web services interfaces to the external clients. You know, OSGI features basically, that's that collection idea of components. And the web service interface developed to provide flight information service using the ESB to support the new capability. Conceptually, what that looks like is that I have this server. You see the server at the top with the red bubbles. The red bubbles represent an instance of each center's flight information service. So even though I physically only have one processor, or I repair redundant processors in one location, Minneapolis, it is instantiating the flight information service for 20 centers in those two processors, and it is physically connected to one center for management purposes, which is Minneapolis. We call that the back-end interface. It's, while it has this same logical interface as the others in terms of using, receiving messages from the ERAM channel, flight data, and then making that available to the outside world. Someplace someone has to keep track of, well, is it up, is it running, what version is it on, does it need to be switched, and so forth. And so that's the management the back-end interface supports. More graphically, in terms of the architecture, over on the left-hand side is the current programs running that support it on the flight data processor. The flight data management OU is our main kernel today. We use these interface applications 1 and 2 to communicate out to our current interfaces with flight data. And we instantiated this new thing called IFS, which was we called it an adapter. And its purpose is to work with the binary data, convert it basically into XML, and transport it across the wire through the secure environment to the SWIM server so that it can then present that data as a service to the rest of the world. And over in the other boxes, you begin to see on the right-hand side, the larger box, the piece parts that would go into providing a ability to request information on a flight, change a flight, delete a flight, versus subscribe to a category of flights, all flights coming through this airspace, all flights flying between these hours, and to be subscribed to that flow of information. So really, that's the plan. We're going to take flight data, and we're going to basically put it out on the web, not that much different than Walmart sells socks. And this is air traffic control. So I didn't want to get into a lot of detail or depth on it, but I want to point out that's the premise. We had some experiences. We had some observations, and I thought I'd bring a few of them to you, and hopefully they'll be useful. How do you do this in an environment, in a culture of critical services and critical systems? And the bigger thing being is that you can already see that the future users are telling you, well, my requirement today is not that, it's 3 nines. 3 nines is pretty easy. Most of these web products can meet 3 nines. Walmart is up most of the time. Of course, when it's down, it's a real pain in the butt because you got no choice but to wait till it comes back. But there it is. But you're already talking about something that looks more like 4 nines, or maybe even 5 nines, the efficiency critical, the same sort of reliability requirements we put upon our air traffic control software. I can see that coming because it's flight data. And we treat flight data internally, and for the purposes of ensuring that controllers have accurate and up-to-date flight data, as a 5-9 reliability issue, 5 nines and an 8. I think we have that here. So why would this flight information data under the SWIM be able to go with these lower categories of 3 nines or even 2 nines and an 8? Why is the awareness information sharing for some users? Certainly, you know, if you were going to look up grandma's flight, certainly that's not going to be a problem. You know, if that in terms of high reliability, high availability, there's no criticality in it. There's no loss of life. There's, you know, kind of inconvenience of, oh, I was hoping to see where mom was. You know, I'm still hoping that maybe she doesn't make it, but nevertheless, some of the services clearly had a future that was a higher availability than was advertised. So we started looking at, well, what's the failure rates of these products? And what do you find when you go to commercial product? And you say, okay, well, let me just look in the documentation. And you go through and say, well, it wasn't in the little manual. Let me get out their CD. There's a lot of information. No, it's not there. Of course not. Commercial products. So you think, well, they must know. So you contact their technical people, and you've got contracts. You're spending big money for this stuff, right? And you ask, and they're like, we don't know. It works. Most of our customers are very happy, and if they're not, then we work with them to get their product working for them. They're a commercial company. They're more of a service-oriented than a performance-oriented type of software. And so it's a different environment. When you look at its product failure rate as best we could determine it, and we calculated it, I'll give you a little bit of information. I won't go into the details. I am not a reliability engineer, so I don't even know or begin to pretend to know how to come up with some of these, but I know some of the factors that go into it, and when you try to do that in this product and in this world, you find yourself quickly overwhelmed with assumptions and approaches and reasonable, you know, thing to do rather than an accurate result. But essentially what we calculated says, well, it cannot be essential 3 nines, you know, down less than 8 to 10 hours a year, and that's probably your experience. You go to Amazon.com, it rarely fails. You know, you almost always get your product. I think I've had it fail once in a couple of years. I buy books probably every month. So it's pretty reliable. But it isn't the reliability we expect in a air traffic system. And if you're a developer, you can't sell that to the government. We don't accept, it'll probably work. You know, it'll be there most of the time, you know, and if not, you just kind of reboot the thing and bring up a new server, and there you go. It'll be back in no time, you know. You can probably fix it in half an hour. But one thing, our operators are not trained in this stuff. That was one of the issues that we spent some time working through is, do we need to start thinking about putting a network certified engineer into each center to address being able to maintain these sort of interfaces and understand how to build a new connection on the fly if they were to have a problem. That's how they do it in the worlds of the major retailers or the major web server corporations. Is they have people that they could build something from nothing as long as you have the kernels of the application written. They'll put it together and find connectivity and get it back out there on the web. But even with this, okay, we think that probably works, right? We can get under 30 seconds switch time, and we have 30 seconds. We might be able to do that. And it'll be down less than 8 to 10 hours on those assumptions. But there's very high uncertainty in those calculations. One of the key things that goes into when you don't know is you say, well, how big is the software? What type of software is it? What is it used for? And what's the size of it? Well, there's millions of lines of codes in these things, and that's one of the things we'll talk about. And you don't use them all, so what should you count? We went out and we looked at, and actually this was the Lockheed Martin that was the company behind doing this, but they went out and they used what's called olo.net to try to find information about code metrics on the Apache programs that underlie the Fuse products. Since the Apache programs were the real kernel heart of the programs, if you get the information on Apache, which is readily available, you can begin to make and surmise some calculations based upon that. Sounds reasonable. So obviously, how you're going to use it, what it's used for, is bigger than the language per se or the technology per se. But some of the constructs are dependent on the language, complex coding, specific elements. What you want to do is eliminate that, though, and get to more or less, I'm using this product to move data, and I'm doing the calculations inside of the known reliable systems. So we try to apply our slot counter and say, okay, well, let's see if we can validate the data we got off of this website. And of course, what you'll find out, and I have a chart here, that's the different languages that are used in the Apache service mix. It's written as an open source by a large number of developers out there in Google land, which I think is just past Obrador on your way out to Fife, including things like Groovy. We love to point out which one is groovier than the other, but one of them is groovier than the other because there's a few more lines of groovy in it. So we say it's groovier. But we don't have slot counting tools and procedures and policies written down for all of these different sorts of things, these scripting languages and so forth. We do in some cases, but in most we don't. So then trying to validate the count that we got off of this website proved challenging because just being able to count the code ourselves. And of course, we're not positive in many cases how much of any of these pieces. Do we use anything groovy in our actual implementation? We don't know. We'd like to be groovy, but we don't know if we are, at least not without doing more deeper research into it. And so then we start saying, well, the parts that probably really matter, right, are the parts that are Java and XML. That's probably the kernel heart of what we're trying to do. We're not trying to do anything real sophisticated. Essentially, this application has data. We're going to send it in an XML format to these programs for it to store, establish a interface for clients to come to and request specific data. When it receives a change, for example, it just has to basically do the amendment, send back an XML into the ERAM where we have something that will turn it back into binary and submit it into the Flight Data Manager. So the real pieces out here, out on this SWIM service, this SWIM server, are not probably all that groovy, and it's probably reasonable to make an assumption that the Java and the XML are the code that matters the most, and so you narrow in. But you can see all the different ways of counting this code, and which is the right one to underlie a reliability calculation or expectation. And again, you might go in the lab and you say, gee, it seems to work pretty well, we never have any major problems, or it's very quick to recover. But you've got to sell that by contract, and they're not allowed to do that. You have to prove and demonstrate that you can meet that while we try to intentionally make it fail as part of your test program. And so as a vendor, you're very, off-put by the fact that, well, in one hand, I have a product that says it's good. You've told me really to use this product. And then you want to hold my feet to the fire to say, prove it works. Well, it wasn't my product. I didn't develop it. So they wanted to do some research and background. And I actually, you can see at the bottom, I think, is this the one? I'll just go forward. I had, when I get to the results, I will. They asked for some tasking. They said, will you give us some tasking to go off and develop a high availability, fault-tolerant prototype using this stuff? And a fault-tolerant message flow. Lossless, ordered, processed serially, right? Efficiency critical, that's the easy stuff, right? That's really that 2 nines, 3 nines type of capability. You know, get me back in 30 seconds, you meet needs. Safety critical is the 5 nines. Don't be gone for more than 6 seconds, or you fail, and you don't get paid. And again, they use the Fuse message broker and use AIX in the IBM Java's developer kit to build their prototype. And they came away saying, well, we tried various iterations, and I didn't go into the details here, but a master-slave configuration, so that I have a ready backup, does seem to work pretty well in the environments. It is possible, I guess it's I'm trying to think of which component it was that in particular was responsible for maintaining that master-slave switchover, but it does work. If you use a distributed file system so that you can take a hit on either server, and that becomes the next challenge, then is to figuring out that file system, right? And if necessary, I can set up a master and several slaves, so I can share the visibility of the database and maintain performance and availability, even in more than one failure configuration. And it provided for a pretty fast recovery. In fact, less than a second in most cases. The biggest problem, I guess, in this, and I'll cut to the chase, the broker depended on disk-based persistence. Trying to get a disk-backed distributed file system that can support concurrency and meet the efficiency critical times, the 5 nines, detect and recover, there are very few options, and they're very costly options. Went out and did a search and research into the enterprise file system providers, found Veritas was one, right? They could, one of the very few, if only, that could commit to a failure detection of less than 20 seconds. The detection of less than 20 seconds. I want to be recovered for 3 nines in 30 seconds, for 5 nines in 6 seconds. Like I say, in most cases, we detect failures in our ADA programs in a nanosecond, in a clock cycle, basically. We very rapidly detect those failures. It's a high priority task to do so. So nothing that they came up with, they said, would meet the safety critical requirements. But we didn't have safety critical requirements at this point. We just wanted to understand how far can it go in terms of the evolvable support for it. So I actually called the person who worked on this the other day before I left and kind of updated my slides a little bit. His name is Scott England Sullivan. He's Lockheed Martin out of Eagan, Minnesota. He's actually a subcontractor there. And he said, well, the real problem isn't that the limitation of the fuse of the ActiveMQ. Any Java enterprise solution that relies on the disk is going to be the problem. A lot of systems don't offer an alternative, and there's a lot of latency in the message flows. What you need is a memory-based distributable data store with persistent storage done in the background on a separate task. Because of the volumes of data that we intend to handle, that was a problem. Now, what he pointed out is that while the prototype couldn't take advantage of this, the latest release of ActiveMQ is called Apollo, is out in beta. And they haven't evaluated it yet for this purpose, but they say it does support using a memory-based persistent storage system. And, but being able to take advantage of that would absolutely be required if you wanted to move up to the higher availability reliabilities. So experience lessons learned, we were able to develop a basic essential level FIS service, 3 nines reliability, using web services. We used a master-slave implementation to provide redundancy for the fault tolerance and for maintenance, because you have to be able to say, well, I'm going to upgrade, make changes, and switch over. For security, we had moved the swim servers outside the boundary and put a security barrier, basically created a realm out there that protected ERAM from them from a security standpoint, and maintained that separation of the mission-critical services and the non-mission critical services, so that non-mission critical services can't clobber the mission-critical services. That allowed the swim components to be decoupled from the internal binary ADA representations. We basically wrote an adapter, an ADA adapter that takes it, rewrites it into an XML schema and sends it over to the swim service. keeping all of the binary representations and ADA sort of representations inside ERAM, and then XML from there out. WSDL is, as I pointed out, if you're not familiar, is basically binds in both sides, the server side, the client side, providing them the server writes it, makes note of usually a registry or some other way of publishing and notifying clients that it's there. The client then acquires the WSDL, builds it in, and that means he has a compatible XML schema to talk to you with and to do. Now, one problem that I pointed out a few times in a few places where we're saying, well, we could use this swim, and I say, well, you know the size of your message in the future? Today, the amount of information they want to share is fairly small, but there's a lot of them. XML is about 10 times more data on the wire than a binary representation of the data. Our trajectories for a fight, which is the detailed, cusps and points and curves and turns and speeds and angles and the fixes and points, can be over a megabyte each. So now I start sending thousands of 10 megabyte messages, and what's going to happen to that wire? And so at this time, we're kind of in a stand down from the future while SWIM kind of refigures out what is their strategy. And in some cases, I think what it is they're stepping back and saying, well, I should not let my scope get pushed out to say I'm going to support 3.9s and 5.9 type programs. 5.9 type programs. I can support 3.9 type programs. The technology is there, the capability is there. The web services does support it with very little difficulty, but trying to push out towards 5.9s is probably not that realistic and probably not appropriate. And then I have to start looking at my services for, well, how much data is this service going to be publishing and consuming? Because I may not be able to afford the phone bill. And easy, I said, is a relative term. I said we were easily able to do it, right? Relative term. There's a number of challenges I wanted to point out that just come from the free and open source software. It's commercial, right? You don't know nothing about it. You don't know how it's designed. You don't know what its implementation is, and you struggle trying to be efficient using it. The source is open, but you have hundreds of authors out there, so you have different coding standards and styles. At one time, I thought, well, this is going to be a killer, and I talked to someone that was involved in the Apache programs. They said, no, we have these standards bodies and groups, and they make sure that everything is done consistent and so forth, right? They're the gatekeepers for any particular component. I went, oh, well, maybe it won't be that bad. I was thinking about it in terms of security at the time, of understanding that there's not security vulnerabilities. I said, I must have a mess in there of, 40 instances of different types of capabilities. Oh, no, we manage all that. Well, turns out that when you actually put a tool to it, I'm right. There's a lot of redundancy, inconsistencies, it's just system admin assumptions, Oh, record this error to a file, structure of the file and so forth. And, well, now I want to collect the data from all of these things, log them together. I've got 40 different formats to pull together into one common logging system later. The web service implementations pull in these very large libraries, a lot of redundant routines, things that do this, obviously the same things, and facilities, and you only need a few or one. But they're part of the library, they're built in. You can't get rid of them easily. One of the things we found and experienced was that some of the FOSS elements, the free and open source software elements, they go to their task and find it busy, and they had the smartness to say, well, give me a new one. Well, if I'm trying to write, important software where I know the state of the system at any point in time, I don't want a piece of software saying, give me a new task. That one's busy. Well, if it's busy and you're not able to get to it, it probably means you're not the priority. Huge problem, obviously, in anything when you're working with somebody else's stuff. I don't know how it works that well, but more important, I don't know how it breaks. And a lot of problems understanding, well, how would this product break, and doing research and finding new failure modes that were not anticipated. And there's a kind of a different mentality in web services. Failure means you couldn't buy the latest Lady Gaga song. but it failed. It's not there. It couldn't get to the website. But ours is, I didn't get the correct service at the time I had requested it. The web server frameworks, rather than being proactive to say, I know when you failed and I can recover you and start recovering you as soon as I detect the failure, they rely upon that client to make a request that doesn't succeed. When it doesn't succeed, he'll make a new request. He'll come in on a different port. And now you'll know that the last one must have timed out and failed. So if you want to know more, you need to go in and put in the hooks to do so. So basically, your availability really isn't known in many cases until it fails, until it is visibly failed. Well, it may have been failed for hours, but there was no traffic on the line, so we didn't see it. So we had to put in basically hooks throughout the code, throughout the web service, the Apache service mix, Apache Camel, all those sort of things, the enterprise service bus, which were basically heartbeats to tell us that I'm okay, I'm okay, I'm okay. Because otherwise we had no way of knowing until the client failed to get an answer. And it's difficult to limit the scope. In Java, when things fail, typically what do? Just kill it all and start it all back up. In an ADA program and high reliability availability, we normally like to say, well, what is the scope of my failure? What really has to be restarted? And I'll leave everything else going and just restart that one piece. It's not a paradigm of, well, flush everything and start over. But that is typically in the Java virtual machine and the Java applications. Doesn't have to be. Is that correct English? Hottest is getting to my brain, I think. It doesn't have to be, but it is kind of the paradigm you see in many parts of the code. You obviously have supportability and lifecycle issues. There's a lot of building blocks and libraries. One of the things we found was that we use Maven, and this is very commonly used in the web service world for building. It's kind of your iMake for this stuff. It uses a thing called project object modules, or POM files. Well, this Maven has no hesitancy to go out on the web looking for its compatible versions and pulling them in, sucking in hundreds and thousands of definitions. Well, in a secure environment, that is not very acceptable. So now you end up having people go through and find the necessary pieces that they really need for dependencies, put them into a directory structure on your build server, and write the POM to say, look there, and get the hell off, stop shopping at Walmart. Don't shop at Walmart. You're only allowed to look in your local server. So you have to make, in addition, the other things, these things change from time to time, so you do have to go out on the web looking and make sure if it's changed and what it means for you. But you do need to make a snapshot, maintain a local file copy for anything that's important, because the next time you go look for it, that version may no longer exist. It may not be there anywhere. It's been replaced by something, may or may not be compatible replacement. And the other issue this creates is that because of all these free open source things in the SVO, you can use them free GNU public license, that sort of stuff, right? But we need to legally, and the developer in particular, because Lockheed Martin just grabbing someone's product and find out, well, I didn't write that to be a public license. Well, it pulled it in. It's your responsibility as a developer to know that you have rights to what you're using. And as the government, we say, we hold you responsible to prove that everything that's in your software you have rights to, and that you explain to us what our rights are or what our restrictions and rights are, and we accept that before we buy the product from you. So that created a huge problem. And it actually was fairly easy to solve in terms of writing the tooling and so forth to collect up all these licenses and collate them, but it had to be done, and it had not been anticipated. Other sort of developer lessons learned, again, I got this from a briefing that Lockheed Martin themselves did. How do you, teaching your developers, becoming familiar with the source code, run write your own unit tests, basically, Java unit tests, in order to understand what's this code doing. Maybe if you know what it's doing, you'll be better able to tell when it's broken, when it failed to do it. If you take a minor update of one of the free and open source products, you sometimes find that there's major changes in it. And you need to immediately evaluate it compared to what was in the last release and whether or not it broke you. It's always been advertised that in the web service world you get 80-20. 80% of the job is configuring, and you just write 20% of the code to glue it all together, make it all work. We kind of found that we're someplace out there in that 80th to 99th percentile world where we end up writing a heck of a lot of code to glue. We're not just gluing, I guess, existing components together. We wanted to do things that are unique and unusual and are not supported out there in the World Wide Web. You can't go buy an air traffic control system off of Amazon.com. We've tried, but it didn't work. So the result is we found we had higher productivity working with this stuff. We developed a lot more code than we thought we would. And the sponsors, if you've ever been in a program with government sponsors or major corporate sponsors, do they ask you, how's it going? They say, what's your SLOC number? Wait a minute, your SLOC number is twice as high as it was last month. Yes, but my cost hasn't gone up. Bullshit. They don't believe it for a minute. They see that number going up and they know what's coming next, which is a request for more money. And so it's hard to explain, well, we're getting double the productivity we were before, but we're writing twice as much code as we thought it would take to do it. And the elephant's tail. I stole this out of someone's presentation many years ago. There it is. And the bottom line, can be done. Higher integrity, high reliability systems, it's not as easy as you think. We found in our environment, our user and system requirements and expectations pushed the design of the web service technologies that we were given. It's not entirely clear that free and open source benefits are worth it in all cases. Providing flight data for initial data communications, our development estimate decreased significantly when we took the swim out. We saved 10,000 lines of code writing a proprietary interface rather than trying to write a web service to provide what they needed. ERAM is not a legacy app. Typically you use a lot of this stuff, this SOA and these sort of things, ideas. Let's wrap that legacy item that no one understands how it works exactly. Just kind of put a wrapper around it so we can get the data out. Well, ERAM wasn't written 10 years ago or 15 or 20 years ago. We're still in the process of finishing it now, but it was just written the last few years. We designed it to be accessible. I can provide you a component from our component architecture, and then you can locally request. So why can't I just remote you and make you look like you're an insider? Go through security, obviously, but I can make you look like an insider no matter where you are in the world, and we can filter and select the data as necessary. And one of the issues I kept wrestling with, and I was just talking about it with Rod before we started, was what are the criteria and attributes that you should apply to this type of product or to any type of commercial or free open source product for being used in the context of various high reliability or medium reliability or low reliability applications. I found we don't have one in our agency, and that's a deficiency. We need to think about it so that we don't get it in place and then say, well, this stuff really doesn't meet our sense of being secure, safe, robust to be used in an application beyond more routine web service type of uses. Who's going to qualify and certify it for that use? Certainly the vendor's not. And I think I just have it do weird things and I come to an end. So any questions?